Hello. In this video, I'm going to use a couple of examples to introduce and motivate some important concepts and terminology that we're going to use in our study of the limits of functions. And asking about the limit of a function is really asking a question of the form this that I have in my first example here. What in the heck is going on with this function around this input x value? That's what a limit is all about. And for this example, I have a specific function in mind, sine of x divided by x, and I have a specific input x value in mind, x equals 0. But any limit, as we're going to learn, asks a question like this. What's going on with this function around this point? So I'm going to hold off on showing you a picture, a graph of this function until the next slide. I just want to do a little bit of investigating first. When I say what's going on with this function around this input, well, your first idea might be let's just plug in that x input into the function. Let's plug in x equals 0. But you run into a big problem with that. In this case, you get sine of 0 divided by 0, or you get 0 divided by 0, and that's undefined. That doesn't have a meaning, that ratio. So what's going on with this function around this point? Aha, well that's why I asked around and not at. If I asked you what's going on at x equals 0, you could say the function doesn't exist, it's undefined. But when I say what's going on around x equals 0, I'm wondering, does the graph of this function approach something? Even though it doesn't exist at 0, if I zoom in nearby, is there a specific pattern? Is there something going on? And so that's what I'm exploring in these calculations down below. I'm plugging in values of x that are close to 0 but positive, and some that are close to 0 but negative. And so you might notice from the calculations in the top half here that as I plug in x values, the inputs to the function that are still positive but getting small, getting closer and closer to 0, it looks like the outputs are getting close to 1. And in fact, pretty rapidly. If I plug in x equals 1, I get an output from the function of 0.84 or so. And if I plug in a tenth or 0.1, I get an output of 0.998, really close to 1. It's a big jump. And then if I plug in 1/100th or 0.01, I get really close to 1, 0.99998. And if I keep plugging in smaller and smaller inputs for x, I will get numbers coming out that are closer and closer to 1, 0.999, a bunch more nines. And in fact, the same thing happens if you plug in small x values that are negative. As I plug in those negative x values that are getting smaller and smaller in magnitude closer to 0, I get a similar pattern where the numbers coming out from the function approach 1. But you may even notice something more specific, that they're exactly the same numbers, they're identical. And there's a reason for that. This is because the sine function has odd symmetry. If I were to graph the sine function, remember it looks like this. And if I have a point on the graph over here, and a corresponding point exists on the graph over here that has the exact opposite x value and the exact opposite y value. That's what the odd symmetry is being described down there. And so as a consequence, that will make this function f of x that we're exploring here have even symmetry. If I were to plug in negative x, the opposite input, well, the top will be the opposite sine, S-I-G-N, because of the S-I-N-E, sine property. I've always hated that word. I wish we had not picked homophones for those, so bear with me. But the top of the fraction will output the negative value of what it did earlier, and meanwhile the bottom of the fraction, the denominator, also has the negative in it. So I would get to cancel those out, and that works out to be exactly positive sine x over x. And so I get the exact same numbers going on here. And in fact, that's why what I'm about to do is to skip to the graph on the next slide. We'll see the function has even symmetry, meaning that it's a mirror image across the y-axis like this. If I have a point on the graph, the opposite x value has the same height y, not the opposite height y, like we did for the odd symmetry. And so let's look at that now. Remember, the main question here is what's going on with this function around x equals 0, knowing, interestingly enough, that it's undefined at x equals 0. So let's look. That's what the graph of that function looks like. And it's not at all easy to see. In fact, you can't. But there really is a hole there. Right at the point where x equals 0, there's a hole. function doesn't output exactly 1 when I plug in x equals 0. In fact, it outputs nothing. I get 0 divided by 0. It's undefined. But still, the values of x around 0 output values of y that are very close to 1. And that's what this notation over here means. Everything that we were observing in our calculations on the previous slide is summarized in that one little green box there. As I let the input x approach 0, the outputs approach 1. And that's how I would read that notation out loud, or in my head in words. The limit of that function, of that expression, the limit of sine of x over x, as x approaches 0, that limit is 1. And so we write equals 1 to say that the kind of the end of this infinite process, the limit, is the number 1. And so those numbers that we were calculating on the previous slide, they get closer and closer and closer to 1. And if I were somehow able to magically complete that process and say, what are they getting closer to, that number is exactly 1 itself. And so that's why we say equals 1. But notice that that's really slightly different from saying that f of 0 is 1, because that's just not true. This function this graph as a whole, the function is undefined at 0. So we write equals there to say that the numbers are getting closer and closer. The outputs are approaching 1. Here's another example of a function, and I want to explore the same kind of question. What's going on with this function around x equals 0? So I'm also using this as hopefully a refresher of what this kind of notation means, this piecewise defined function. Now by piecewise I mean, well, there's two pieces of the domain. And so if you need a little refresher of that concept, of this notation, what it means, think of this as saying the domain of this function has two pieces. And you should also remember that by the domain of a function, I mean the set of inputs that I could plug into the function. So in this case, it's a piecewise function because the domain is split into two pieces. And there are different formulas telling me what the function outputs. And it matters, it depends on which piece of the domain the input x came from. So this notation is telling me that if the input x was negative, if it came from that piece of the domain, then my function is going to output negative 2. So if I start to sketch a graph of this function over here, this is saying that for negative x's, for inputs over here, the output is going to be negative 2. So I'm just going to start drawing that graph. It's a horizontal line at the y value negative 2. And that's only up until 0. If x is strictly less than 0, that's when this happens. But at exactly 0, it doesn't output that. So I'm going to put a little hole there to say, at x equals 0, I don't know yet that the function outputs negative 2. It certainly doesn't do that because of this piece of the domain, because I'm only talking about x is less than 0. All right, for the other piece of the domain, for x's that are greater than or equal to 0, it says output x. Or in other words, I'm just going to draw the graph of the function y equals x, which I know is a straight line with slope 1. And I'm going to do that for all of the inputs x that are positive or 0. So that's why I have that filled in dot there and not a hole like I did down there. So now my question of what's going on around x equals 0 is a little different than the previous example. One major difference between this and the previous example is that f of 0 is defined. It does exist. It's not like the last one where f of 0 just doesn't have a meaning. And here, f of 0 is 0, because the input x equals 0 belongs to this second piece of the domain, and plugging it in there, I get 0 as an output. So that's not the problem here, that's not the issue. But what I notice is that what's going on around x equals 0, all of a sudden it matters whether I'm getting close to 0 from the positive side or from the negative side. And so as the input x approaches 0 from the right, or if I plug in really, really small positive values for x, the outputs of the function are approaching a y-coordinate of 0. And remember, that's independent. That's a little different from saying that f of 0 is exactly 0. That's a different question. I'm saying if I plug in positive, really small numbers, the outputs do get really close to 0. And it doesn't matter whether it actually gets there or equals 0 at any point. I can still say that as x approaches 0 from the right, from the positive side, the function approaches outputting 0. And meanwhile, on the other side of x equals 0, what's going on around over there to the left? Well, as x approaches 0 from the left, from negative values, the output f of x approaches a height of y equals -2. If I'm traveling along this horizontal line, I'm going to bump towards that point right there, at the height -2. And so this is different from the previous example where the same thing was happening on both sides. Here I have different things happening on both sides. And so for this reason, we're going to say that this limit doesn't exist because there's two different things going on. And we're actually going to have some ways of writing that down in mathematical notation using limit notation. And so these two notations down here are the ways that we'll write the two observations we've made about the function to the left and to the right of 0. Notice that when I talk about x approaching 0 from the right, from positive numbers, we're going to use that little superscript plus to indicate that. And when I'm talking about x approaching 0 from the left, from the negative numbers, I'm going to use that little negative superscript to indicate that. I can see that those are two different results. One of the limits produced 0, one of them produced a -2. And because those results are different, that's why we're going to say, well, the limit does not exist, because those are two different outputs. So speaking of limits not existing, here's another example, a really striking example of a limit that does not exist. And so I feel like I have to make an obligatory reference to Mean Girls and being so excited about the limit not existing. If you have no idea what I'm talking about, or even if you do and you want to see that scene again, you can follow that YouTube URL at the top there, or just Google Mean Girls limit does not exist. It should be the first thing that pops up. And I can't recommend that movie enough for those of you listening. So anyway, here's another function, and you can see it's very strange, crazy graph there on the right, unlike anything we've seen before, at least in this class. And I'm going to try to explain briefly here why this limit does not exist as well, but for a very, very different reason than what we were just seeing. Essentially, in the example before, approaching 0 from the left or from the right gave very clear answers. They just happen to be different answers. Approaching from the right, the graph shoop, goes right down to 0. And approaching from the left, shoop, goes right there to -2. There's no uncertainty about that. The problem was that those were two different numbers. But over here in this example, yikes. Well, this graph doesn't appear to be doing anything understandable or coherent around x equals 0. So this question of what's going on there is a really deep one. There's a lot going on. So I'm going to recommend you pausing the video for now, following this Desmos URL, or just going to graph this function yourself. The only difference between what you're going to do and what I have in the Desmos tool is I've already set up those points that you can see marked on the graph, and you can see how I did that. But you can just graph this function on a fresh sheet yourself, and just kind of explore, zoom in around x equals 0, try to convince yourself whether or not this limit exists, like what really is going on around x equals 0. So here's the problem. As it turns out, this function is approaching a whole bunch of different things around x equals 0. It's, in some sense, approaching all the possible numbers between -1 and 1 inclusive. It's approaching all of them at the same time, and that's just too much stuff happening, and that's going to be essentially the reason why we declare that this limit does not exist. So I'm going to have us evaluate this function at some very particular input x's, and we'll be able to output those values based on what we know about the cosine function, and we'll notice some patterns, and we'll see where these dots are in the graph that I've already marked for us. The first thing that I'll have us plug in is x equals 1, and I can see that f of 1 is cosine of pi over 2 times 1, so cosine of pi over 2. Remember that that means 90 degrees. Pi over 2 radians is a quarter of the way around a circle. It's a 90-degree angle, and the x-coordinate of that point is 0. That's why the cosine of that angle is 0. That's a really quick refresher on cosine in the unit circle, so if you really need to explore more about that, definitely go do that review. But for right now, I'll trust that you know what I mean when I write this down. And that's exactly what this point over, oh, sorry, not that one, this one over here on the graph is. When x is 1, y is 0. That's that point there. When I plug in x equals 1/2 instead, that's going to be this point down there, I get f of 1/2. It's cosine of pi over 2 times half, or pi over 1, or just pi. And again, pi is halfway around the circumference of the unit circle. It's a 180-degree angle. That point over there on the unit circle has an x-coordinate of -1. That's why the cosine output is -1. And then when I plug in x equals 1/3, I get cosine of pi over 2 times 1/3, or cosine of 3 pi over 2, and that's a 270-degree angle. 1, 2, 3 pi over 2 is there, and if I plot that point on the unit circle, its x-coordinate is 0. That's why the cosine of that angle is 0. And so there I've plugged in the next 4 input values along this pattern, 1/5, 1/6, 1/7, and 1/8. And you can see that they're going to cause me to evaluate cosine of 5 pi over 2, and 6 pi over 2, and 7 pi over 2, and 8 pi over 2. And that's why I keep writing that, for example, instead of 4 pi, instead of simplifying it. To me, this is simpler. I can actually see the pattern. I can see what's going on. I don't care that that equals 4 pi. Sorry, just a little mini rant about simplifying and how much I hate that verb. But anyhoozle, notice that I'm following the same pattern of points on the curve. I get 0, and then -1, and then 0 and 1. And if I keep following this, if I do a 9th, a 10th, 11th, and a 12th, I'm just going to go 0, -1, 0, 1. And I'm going to keep going up and down between -1 and 1. And I'm going to do that so rapidly around x equals 0. If I keep continuing this sequence of points, they're going to approach 0. So as x goes to 0, the y values don't really approach anything at all. They keep oscillating wildly between -1 and +1. As x approaches 0, y oscillates rapidly from -1 to +1. And the same thing would happen if I were to plug in negative values like this, and I can see that that's happening over there on the left half of the graph too. And so that's what's going to cause me to say that this limit does not exist. And so really I'll sum up that conclusion as what I've written there in the very top right. That limit does not exist because the output of the function doesn't approach a specific value, one specific number. And it's going to be one of the reasons that we'll have limits not existing.